Welcome back. If you made it this far through the course, well done. We've already discussed the most widely used techniques for hyperparameter optimization. So in this video, I want to wrap up what we discussed and hopefully offer a few guidelines on when you could use each technique. In the course, we discussed two broad strategies of searching hyperparameters. Those that I called basic search strategies that include manual search, grid search, and random search. And then we discussed sequential model-based optimization or Bayesian optimization. And within these methods, we discussed GPs, SMAC, and TPE. Now, these techniques have some advantages and some disadvantages. For example, we've seen that grid search and random search are fully parallelizable because each hyperparameter combination is evaluated independently of the others. So we can run all the models in parallel. But Bayesian optimization is not fully parallelizable because Bayesian optimization capitalizes in selecting hyperparameters based on the evidence that we have so far. So it is in essence a sequential search, but we can parallelize some searches in order to speed things up, and then there is of course a trade-off. The more we parallelize, the less we capitalize on the sequential advantages of Bayes optimization. We also discussed that random search is effective in high dimension. This is when we have a lot of hyperparameters, and so is Bayesian optimization. But grid search is not. On the other hand, grid search is effective in very low dimensions, whereas the other ones are not really designed to work with very few hyperparameters. And here notice that I put very low dimension in brackets, because as time passes and we use more and more complex models, what before was a low dimension, now it's a very low, and what here I call high dimensional spaces, when we train very complex neuronal networks, this is actually not so high dimensional spaces because we can have even higher dimensional spaces. So some people would argue that Bayesian optimization is useful in moderate dimensional spaces instead of very high dimensional spaces. But we will discuss that later on. Both random search and Bayesian optimization are suited for continuous hyperparameters, as well as categorical and discrete, but grid search is not. And this is because the hyperparameters in grid search are defined by the user manually, so the user only inputs a certain number of different values per hyperparameters. But when we set up a random search or a Bayesian search, we extract hyperparameter values from distributions. Therefore, these two searches are able to explore a wider range of values compared to grid search. And this makes these searches more effective. So, as we said, grid search is effective in very low dimension, whereas the other ones are designed to work with more high-dimensional models. This is more complex machine learning models. So Bayesian optimization is designed to determine the best hyperparameters for more complex machine learning models, that is, models that take more computational time to train, because we approximate the hyperparameter response function with a surrogate. So we don't really need to train so many models like we would with random search. And here notice that I put ish instead of that is not suitable, because as time passes and we have more computational resources at our disposal, performing multiple searches at random becomes easier and easier. So random search is resource intensive, because we train multiple models at the same time. So we need a lot of computational resource in order to capitalize on a random search. whereas Bayesian optimization is not, because in essence we are training one model after the other or a few models after the others. This means that random search is not very wall clock time intensive. This means that it doesn't really take a lot of time to find the best hyperparameters. It just takes a lot of computers. But if we have all the computers running simultaneously, then we can find the best hyperparameters in shorter time compared to Bayesian optimization that uses less computers but runs the models one after the other, so we need to wait until the models are all trained. So we discussed 3 different Bayesian optimization approaches. One is the one based on Gaussian processes, the one based on random forests, and TPE. So these techniques differ in what they are approximating. Gaussian processes and SMAC are approximating f of x. This is the hyperparameter response function, whereas TPE is approximating the hyperparameter distributions. To approximate these models, Gaussian processes uses, of course, Gaussian processes, SMAC uses random forests, and TPE uses density kernels, which are also known as 3-person estimators, and therefore the name. Now, for this reason, because of the way they are designed, GP and SMAC capture hyperparameter interaction because they evaluate all the hyperparameters together within or through the hyperparameter response function, but TPE does not, because TPE looks independently at each hyperparameter distribution. Now, in terms of how long these models take to compute, SMAC and TPE have been shown to be the fastest, and Gaussian processes are not so fast because it takes a little bit longer to compute Gaussian processes. GP and SMAC are implemented in the library scikit-optimize, and TPE is available in Hyperopt and Optuna. And something that is very important and is probably going to guide our decision to use each one of these techniques is that TPE supports nested spaces because of its design, that it looks at each hyperparameter individually, but GPs and SMAC do not. Now, in terms of performance, some scientists have compared these 3 algorithms across various models, and they have concluded that almost always SMAC works best, so finds models or finds hyperparameters that return models that perform best. GP comes in the 2nd place, and TPE comes in 3rd place. And we're going to have a look at some results in a second, but first I want to bring into the picture random search. And I want to just highlight that random search also captures hyperparameter interactions. And it is implemented in very many different libraries. And if we use the implementations in Hyperopt and Optuna, we can also run random search in nested spaces. And in terms of performance, random search can return a model with the best hyperparameters, provided we allow sufficient number of iterations. So in other words, some scientists have shown that if we run a big enough number of hyperparameter combinations, random search can indeed find the best hyperparameters. So these are the results that these scientists have observed when comparing SMAC with the GP implementation in this package that is called Spearmint, and also TPE as it is implemented in Hyperopt. They have used neural nets. They have also compared in what they call low-dimensional models that, as you can see, are logistic regressions, linear discriminant analysis, and support vector machines. So these models tend to have fewer hyperparameters compared to neural networks. And they concluded that SMAC works better than the other models in low-dimensional spaces, and also SMAC and GP tend to work best in higher dimensional spaces, and TPE tends to return overall the worst performance, or tends to find less optimal hyperparameters, if you will, and the author thinks that this is because TPE cannot contemplate hyperparameter interactions. Having said this, if we look at the actual error values, we can see that across the different models, they are fairly similar. So it doesn't really matter which model we use. Any of these models should allow us to find good enough hyperparameters. So which method should we use? If we're training a scikit-learn model, I would say that almost always the random search that we can also find within the scikit-learn package is going to give us the best solutions if we allow a sufficient number of iterations or searches. Alternatively, we can use Bayesian search through the scikit-optimize package. Remember that scikit-optimize offers a wrapper that allows us to run a Bayesian search as if we were running a random search with the randomized search optimizer from scikit-learn. If we're training other models that are not in the scikit-learn package, for example XGB or LightGBM, I would suggest to start with random search, and we can do this using scikit-optimize or Optuna. And if we want to use a Bayesian optimization, we should probably try SMAC because it has been shown, or it is thought, to outperform GP and TPE based Bayesian optimization methods. If we have nested spaces, so if we want to search hyperparameters for different models, or if we're training neuronal networks where spaces come baked into some other spaces, depending on the complexity, we can try random search implemented in Optuna or HyperOpt, because these are the packages that support nested spaces, or alternatively TPE, also in these two packages. And if we're training neural networks, most likely we're going to end up using TPE or other methods that we will discuss later on that come baked into Optuna, Keras Tuner, RayTune, and some more. So, the methods covered so far, I think will capture 90% of the models that most of us are going to be working with. So if we are working with basic regression classification models, off-the-shelf algorithms from the scikit-learn package or other libraries like GBM or XGBoost, or if you're training basic neuronal networks, I think any of these techniques should help you find the best hyperparameters. Now, if you're really short on computer resources and you need to reduce the time it takes to search for hyperparameters, or if you're building very complex neuronal networks, then there are other more specific methods that have been developed, and we will discuss those in the coming sections. That is all for this section, and I will see you in the next one.